Together we advance science. Together we achieve greatness. Imagine two different types of beads strung together on the same chain. That's a copolymer. The future of material science is bright, and irradiation is just one of the many tools that researchers have at their disposal. By using copolymers with high swelling ratios, we can significantly reduce the concentration of harmful substances in the water. Clean water is vital for all forms of life, and by improving our wastewater treatment processes, we are taking a crucial step towards a more sustainable future.
Guess what? Adsorption is stepping up to the challenge, particularly in the development of advanced energy storage technologies like hydrogen storage. Hydrogen, with its high energy density and zero emission potential, holds immense promise as a clean fuel source. However, storing hydrogen safely and efficiently remains a key hurdle. And these MOFs act like molecular storage units, capable of absorbing and storing large amounts of hydrogen within their porous structure. Imagine a tiny apartment building with countless rooms, pores, each capable of accommodating a hydrogen molecule. This high storage capacity, coupled with the reversible nature of adsorption, makes MOFs frontrunners in the quest for efficient hydrogen storage solutions.
Welcome to our YouTube channel for Science Salah Lotfy. Today we're going to discuss an exciting research paper published in Polymer Bulletin, which addresses a crucial topic: free radical polymerization of polyvinyl butyral polyethylene glycol diacrylate, copolymer for removing organic dyes from wastewater. Let's start by introducing the key researchers and the research institutions they are affiliated with. The first researcher is Professor Dr. Salah Lotfy from the Polymer Chemistry Department, National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, Cairo, Egypt. This center is one of the leading research institutions in Egypt, conducting advanced research in polymer chemistry and its various applications. The second researcher is Professor Dr. Manal Fawzy Abou Taleb from the Chemistry Department, College of Science and Humanities, Prince Satam bin Abdul Aziz University, Al-Kharj, Kingdom of Saudi Arabia. Prince Satam bin Abdul Aziz University is one of the leading universities in Saudi Arabia, dedicated to promoting scientific research and development across various fields. It is also noteworthy that Professor Dr. Manal Fawzy Abou Taleb is a member of the esteemed institution, the Polymer Chemistry Department at the National Center for Radiation Research and Technology, Egyptian Atomic Energy Authority, in Cairo, Egypt. This paper was received on March 25, 2017, revised on September 13, 2017, and accepted on September 16, 2017. The research was published in Volume 75 of the Polymer Bulletin, spanning pages 2,865 to 2,885 in 2018. We hope you enjoyed this quick overview of the key researchers and their affiliated institutions. Don't forget to like the video and subscribe to our channel for Science Salah Lotfy for more exciting research showcases. Thank you for watching, and we'll see you in the next video.
Hey there, science fans, let's talk about something super important: clean water. It's essential for all life on Earth, from the tiniest microorganism to the biggest whale. We drink it, cook with it, and use it to grow our food. It's a precious resource, and we need to protect it. But here's the thing: our water sources are facing a big challenge: pollution. Industries, agriculture, and even our homes produce wastewater that often contains harmful substances. These pollutants can contaminate our rivers, lakes, and oceans, putting both human health and the environment at risk. We're talking about things like chemicals, heavy metals, and even dyes from textile factories. These pollutants can have serious consequences, disrupting ecosystems and making water unsafe for drinking or irrigation. That's why scientists and engineers are working hard to find ways to clean up our wastewater and protect our precious water resources. And that's where the fascinating world of copolymers comes in. Wastewater is like a big, messy soup of pollutants. It's everything we flush down the drain, plus runoff from streets and industrial sites. Think about it: leftover food, soap, detergents, chemicals, it all ends up in our wastewater treatment plants. But here's the problem. Conventional wastewater treatment methods often struggle to remove certain pollutants, especially dyes. These dyes, often used in textile and other industries, can be very persistent in water, and some are even toxic. That's where advanced treatment technologies come in. Scientists are exploring innovative materials and methods to remove these stubborn pollutants from wastewater. And one promising area of research is in the use of copolymers. These amazing materials, with their unique properties and versatility, have the potential to revolutionize the way we treat wastewater and ensure clean water for everyone. Let's talk about dyes. They're what give our clothes, furniture, and even some foods their vibrant colors. But when these dyes end up in our wastewater, they can cause a lot of problems. Firstly, they're aesthetically unpleasing. Imagine a river running blue or green. It's not exactly a pretty sight, but more importantly, some dyes can be toxic to aquatic life, disrupting ecosystems and harming the delicate balance of nature. And here's the challenge. Dyes are designed to be long-lasting, which means they don't break down easily in the environment. They can persist in water bodies for a long time, posing a long-term threat to aquatic ecosystems and potentially even human health. That's why finding effective ways to remove dyes from wastewater is crucial. And that's where the amazing properties of copolymers come into play. Now, let's dive into the world of copolymers. Imagine tiny chains of molecules like beads on a string. These chains are made up of different types of monomers, which are like the individual beads. Copolymers are special because they combine the properties of their different monomers, creating materials with unique characteristics. Think of it like mixing different colors of paint to get a whole new shade. This versatility makes copolymers incredibly useful in a wide range of applications, from packaging and adhesives to biomedical devices, and in the fight against water pollution, copolymers are emerging as powerful allies. Their ability to bind to specific pollutants like dyes makes them ideal candidates for wastewater treatment. It's like they have a special attraction to these unwanted guests, grabbing onto them and removing them from the water. But how do we create these amazing copolymers? One common method is called free radical polymerization. It's like a chain reaction, where we start with our monomers and a special ingredient called an initiator. The initiator acts like a spark, creating free radicals. These are highly reactive molecules with an unpaired electron. These free radicals then attack the monomers, causing them to link together and form a growing polymer chain. It's like a game of molecular dominoes where one reaction triggers the next, leading to the formation of long, chain-like molecules. This process allows scientists to create copolymers with specific properties by carefully selecting the types and ratios of monomers used in the reaction. It's like having a molecular toolbox, where we can choose the right tools to build the perfect copolymer for the job. Another fascinating way to initiate polymerization is by using gamma irradiation. Gamma rays are a type of high-energy electromagnetic radiation. They're like tiny bundles of energy that can penetrate through materials, including our monomer mixtures. When gamma rays interact with the monomers, they can knock off electrons, creating those reactive free radicals we talked about earlier. These free radicals then initiate the polymerization process, just like in free radical polymerization. Gamma irradiation offers some advantages over traditional chemical initiators. For one, it's a clean process that doesn't require the addition of extra chemicals to the reaction mixture. Plus, it can be used to create copolymers with unique properties that might be difficult to achieve using other methods. It's like having a superpower that allows us to manipulate molecules and create materials with extraordinary capabilities. The amazing thing about copolymers is that we can design their structure to have specific properties. Remember those monomers, the building blocks of copolymers? Well, by choosing different types and arranging them in various ways, we can fine-tune the properties of the resulting copolymer. Think of it like building with Legos. We can use different shapes and sizes of bricks to create all sorts of structures. Similarly, we can use different monomers to create copolymers with different properties. For example, we can control the copolymer's solubility, hydrophobicity, how much it repels water, and its ability to bind to specific molecules. This level of control allows us to create copolymers that are tailor-made for specific applications like removing dyes from wastewater. The physical and thermal properties of copolymers play a crucial role in their effectiveness as adsorbents materials that can attract and hold on to other molecules. For example, the surface area of a copolymer is important. A larger surface area means more sites for dye molecules to bind, leading to higher adsorption capacity. Similarly, the porosity of a copolymer, or how many tiny holes it has, can also affect its adsorption properties. Think of it like a sponge. A sponge with more pores can absorb more water. Similarly, a copolymer with higher porosity can absorb more dye molecules. Thermal stability is also important, especially if the wastewater is hot. We need to make sure the copolymer can withstand the temperature without breaking down. It's like designing a superhero suit that can withstand extreme heat. One of the key parameters we look at when evaluating copolymers for dye removal is their adsorption capacity. This refers to the maximum amount of dye that a given amount of copolymer can absorb. It's like figuring out how many passengers a bus can carry. The higher the adsorption capacity, the more efficient the copolymer is at removing dyes from wastewater. Scientists are constantly working to develop copolymers with higher and higher adsorption capacities. They do this by experimenting with different monomer combinations, polymerization methods, and even by modifying the surface of the copolymers to enhance their dye binding abilities. It's like a friendly competition to see who can design the most efficient dye-removing copolymer. Using copolymers for dye removal offers significant environmental benefits. Firstly, it's a sustainable approach. Unlike some traditional methods that involve using harsh chemicals, copolymer adsorption is relatively environmentally friendly. The copolymers can be regenerated and reused multiple times, reducing waste and minimizing the need for fresh materials. It's like having a reusable water filter that can clean water over and over again. Secondly, copolymer adsorption can help protect aquatic ecosystems by removing harmful dyes from wastewater before it's released into the environment. This helps preserve the delicate balance of our rivers, lakes, and oceans, ensuring a healthier planet for all. It's like giving our planet a much-needed detox. The potential of copolymers in wastewater treatment is immense. As research continues and our understanding of these versatile materials grows, we can expect to see even more innovative applications in the future. One exciting area of development is the creation of biodegradable copolymers. These materials would break down naturally in the environment after use, further minimizing their impact. Another promising direction is the development of copolymer-based membranes for water filtration. These membranes would act like highly selective sieves, allowing water to pass through while trapping pollutants like dyes. The future of clean water is bright, and copolymers are leading the way. By harnessing the power of chemistry and materials science, we can develop sustainable solutions to protect our precious water resources for generations to come. Our world thrives on clean water. It is the lifeblood of our ecosystems, essential for the survival of countless species, including humans. Clean water supports agriculture, industry, and our daily lives. Yet, industrial processes often release harmful pollutants into our water systems. Factories and plants discharge a variety of contaminants, including heavy metals, chemicals, and dyes, which can severely degrade water quality. Dyes, used extensively in industries like textile and paper manufacturing, are a major source of contamination. These industries rely on vibrant colors to produce appealing products, but the byproducts of these processes can be devastating to the environment. These vibrant compounds pose a serious threat to aquatic life and human health. Aquatic organisms can suffer from reduced oxygen levels and toxic exposure, while humans face risks from consuming contaminated water and food. Traditional wastewater treatment methods often struggle to effectively remove these persistent dyes. Conventional processes may not break down the complex chemical structures of dyes, leading to their accumulation in water bodies. This is where the fascinating world of materials science comes in. Researchers are developing advanced materials and techniques to tackle the challenge of dye removal. Scientists are exploring innovative solutions like using special materials to capture and remove these dyes from wastewater. These materials can absorb or degrade dyes, making the water safer for release into the environment. This essay delves into the exciting realm of experimental methods used to develop and characterize these dye-removing materials. Techniques such as adsorption studies, photocatalysis, and membrane filtration are being investigated. We will unravel the science behind these methods and understand their significance in advancing wastewater treatment technologies. By improving our ability to remove dyes, we can protect ecosystems and human health. Join me on this journey as we explore the intricate processes involved in creating a cleaner, more sustainable future. Through scientific innovation and dedication, we can develop effective solutions to ensure our water remains pure and life-sustaining for generations to come. Imagine a microscopic web, intricately woven with precision and purpose, capable of trapping dye molecules with remarkable efficiency. This is the essence of our dye-removing material, a sophisticated copolymer network designed to capture and hold onto these molecules. We construct these networks using two key ingredients, polyvinyl butyral or PVB, and polyethylene glycol diacrylate or PEGDA. These compounds are carefully chosen for their complementary properties. PVB, derived from vinyl alcohol, forms the backbone of our network. It is the fundamental structure that holds everything together. Think of it as the main chain, providing structural integrity and ensuring the network remains stable under various conditions. PEGDA, on the other hand, acts as the cross-linker. It plays a crucial role in connecting the PVB chains. Picture it as bridges connecting different PVB chains, forming a three-dimensional mesh that enhances the material's ability to trap dye molecules. We carefully select these materials for their unique properties. PVB and PEGDA each bring something special to the table. PVB is known for its film-forming abilities and good adhesion. This means it can create a uniform layer that sticks well to surfaces. PEGDA, with its flexible polyethylene glycol chains, introduces hydrophilicity, attracting water molecules. This property is essential for the material's interaction with aqueous environments. The source of these materials is critical. We meticulously select high-purity compounds to ensure the effectiveness of our solution. We ensure high purity to avoid interference with our experiments. Any impurities could compromise the performance of our material. This ensures the reliability and accuracy of our findings. By maintaining strict quality control, we can trust the results of our experiments and the performance of our dye-removing material. Dyes, the very substances we aim to capture, come in a dazzling array of colors and chemical structures. In our experiments, we focus on specific dyes commonly found in industrial wastewater. These dyes, carefully chosen for their representative nature, help us understand how effectively our copolymer networks remove them from water. Water solubility is a key characteristic of these dyes. They readily dissolve in water, making their removal even more challenging. Imagine trying to pick up tiny, dispersed ink particles from a glass of water. Understanding the properties of these dyes, such as their solubility and chemical structure, is crucial. This knowledge guides us in tailoring the design of our copolymer networks for optimal dye capture. Creating the copolymer networks involves a carefully orchestrated process. First, we prepare separate solutions of PVB and PEGDA in a suitable solvent. The solvent, chosen for its ability to dissolve both components, ensures a homogeneous mixture. Next, we mix these solutions in specific ratios. The ratio of PVB to PEGDA dictates the network's properties, such as its mesh size and flexibility. Imagine adjusting the spacing and thickness of threads in a fishing net to target specific fish sizes. Finally, we expose the mixture to gamma radiation. This crucial step initiates a process called polymerization, where the PVB and PEGDA molecules link together. Gamma rays, with their high energy, act as tiny matchmakers, forging bonds between the building blocks and forming the intricate copolymer network. Section 5. Gel fraction analysis, measuring network formation. How can we be sure that our synthesis process is successful? Gel fraction analysis comes to the rescue. This method allows us to determine the extent of network formation, a critical parameter for assessing the material's effectiveness in dye removal. The process involves submerging a weighed sample of the synthesized material in a solvent. The solvent washes away any unreacted PVB or PEGDA, leaving behind only the cross-linked network. We then dry and weigh the remaining material. The gel fraction, expressed as a percentage, represents the proportion of the material that has formed the desired network. A higher gel fraction indicates a more extensive network, potentially leading to enhanced dye capture. Section 6. Swelling studies, understanding water interactions. Water, the very medium we aim to purify, plays a crucial role in the performance of our copolymer networks. Swelling studies help us understand how these networks interact with water, providing valuable insights into their dye removal capabilities. In this method, we immerse dried samples of the copolymer network in water. The network, with its hydrophilic PEGDA components, absorbs water and expands. We carefully measure the weight gain of the swollen network. The swelling ratio, calculated from the weight difference, quantifies the material's water absorption capacity. A higher swelling ratio suggests a greater ability to accommodate water molecules within the network, potentially facilitating dye capture. Section 7. Thermogravimetric Analysis Probing Thermal Stability. Wastewater treatment processes often involve elevated temperatures. Therefore, understanding the thermal stability of our copolymer networks is paramount. Thermogravimetric analysis, or TGA, allows us to assess their behavior at different temperatures. In TGA, we gradually heat a sample of the material and continuously monitor its weight loss. This weight loss profile provides valuable information about the material's decomposition temperature, a crucial parameter for determining its operating temperature range. A thermally stable material will exhibit minimal weight loss up to a certain temperature, indicating its suitability for high-temperature applications. This knowledge ensures that our copolymer networks can withstand the harsh conditions of wastewater treatment. Section 8. Differential Scanning Calorimetry Unveiling Thermal Transitions. Differential scanning calorimetry, or DSC, delves deeper into the thermal properties of our copolymer networks. This sophisticated technique is pivotal in understanding how materials respond to changes in temperature, which is crucial for a wide range of applications. This technique allows us to identify and characterize thermal transitions, such as glass transition temperature, which provides insights into the material's flexibility and chain mobility. By analyzing these transitions, we can predict how the material will behave under different thermal conditions, ensuring its suitability for specific applications. In DSC, we heat a sample of the material and a reference material at a controlled rate. This controlled heating is essential to accurately capture the thermal behavior of the sample, providing precise data that can be used to enhance material performance. The instrument measures the difference in heat flow between the two, revealing any thermal events occurring within the sample. These thermal events can include melting, crystallization, and other phase transitions that are critical to understanding the material's properties. The glass transition temperature, or TG, a characteristic temperature at which a polymer transitions from a glassy to a rubbery state, is a valuable parameter obtained from DSC. This transition is particularly important for applications where the material needs to maintain its integrity under varying temperatures. A lower TG generally indicates greater flexibility, which can influence the network's ability to interact with and capture dye molecules. This flexibility can be advantageous in applications requiring high elasticity and adaptability, such as in coatings, adhesives, and flexible electronics. Understanding these thermal transitions helps in designing materials with tailored properties for specific industrial needs.
Scientific research is a journey of discovery, collaboration, and immense dedication. Today, we want to take a moment to express our heartfelt gratitude to someone who has been pivotal in our journey. Prof. Lobna Abd El-Wahhab, the former dean at the National Center for Radiation Research and Technology in Cairo, Egypt, has been an invaluable consultant on our thermal analysis.
We are immensely grateful for her contributions.
Her insights have been a beacon of guidance for us all.
Her expertise and guidance were crucial in helping us understand and interpret the thermal properties of the copolymers we prepared.
Prof. Lobna's contributions have significantly enhanced the quality and depth of our research.
Thank you, Prof. Lobna, for your unwavering support and dedication. Your insights have made a profound impact on our work.
Together we advance science. Together we achieve greatness. Water, the elixir of life. We need it to survive. But our industries often taint this precious resource. Dyes especially pose a significant threat. These colorful chemicals, used in textiles and other industries, often end up polluting our water sources. Traditional wastewater treatment methods struggle to remove these persistent pollutants. We need a solution, and that's where the fascinating world of polymers comes into play. What are polymers? Think of them as long chains of repeating units, like beads on a string. These chains can be engineered to attract and bind to specific molecules. In the case of wastewater treatment, we're interested in polymers that can capture and remove those pesky dye molecules. This ability makes polymers powerful allies in the fight for clean water. Now, let's talk copolymers. Imagine two different types of beads strung together on the same chain. That's a copolymer, a polymer made up of two or more different monomers. This diversity gives copolymers an advantage. We can tailor their properties by carefully selecting the monomers. This customization allows us to create copolymers that are exceptionally good at capturing specific types of dyes. The future of clean water is looking brighter already. Molecular weight, in simple terms, refers to the length of the polymer chain. Think of it like this. A longer chain has more beads. In the world of polymers, size matters. The molecular weight of a copolymer can significantly influence its ability to remove dyes from water. Generally, higher molecular weight copolymers are better at grabbing onto dye molecules. Why? They have more sites available for binding. Section 5. Irradiation zapping polymers into action. Now, irradiation might sound a bit intimidating, but it's simply a way of using radiation to alter the properties of materials. This technique has been around for quite some time and has proven to be incredibly versatile in various scientific fields. When it comes to copolymers, irradiation can be incredibly useful. Copolymers are materials made from two or more different types of monomers, and their properties can be fine-tuned for specific applications. It can create links between polymer chains, thereby making the material stronger and more resistant to degradation. This process, known as cross-linking, is essential for enhancing the durability and longevity of the material. This process, known as cross-linking, can significantly enhance the copolymer's ability to withstand the harsh conditions often found in wastewater treatment plants. Wastewater treatment plants are environments where materials are exposed to a variety of chemicals, high temperatures, and mechanical stresses. By cross-linking the polymer chains, we can ensure that the copolymers maintain their integrity and performance over extended periods. This is crucial for applications where reliability and durability are paramount. Scientists and researchers are continually exploring new ways to optimize this process. They are investigating different types of radiation, such as gamma rays, electron beams, and even ultraviolet light, to achieve the desired effects on copolymers. Advanced laboratory equipment allows for precise control over the irradiation process, ensuring that the copolymers are treated uniformly and consistently. This level of control is vital for producing high-quality materials that meet stringent industry standards. The real-world applications of irradiated copolymers are vast. Beyond wastewater treatment, these materials are used in medical devices, automotive parts, and even in the aerospace industry. Their enhanced properties make them ideal for use in environments where traditional materials would fail. In the medical field, for example, irradiated copolymers are used in implants and prosthetics. Their increased strength and resistance to wear and tear ensure that these medical devices can function effectively for longer periods, improving patient outcomes. In the automotive industry, these materials are used in components that need to withstand high temperatures and mechanical stresses. This includes parts like engine gaskets and seals, which are critical for the safe and efficient operation of vehicles. In the aerospace sector, the durability and lightweight nature of irradiated copolymers make them ideal for use in aircraft and spacecraft components. These materials help reduce weight while maintaining structural integrity, which is crucial for performance and fuel efficiency. As research continues, the potential for irradiated copolymers only grows. Scientists are constantly discovering new ways to enhance these materials, opening up even more possibilities for their use in various industries. The future of material science is bright, and irradiation is just one of the many tools that researchers have at their disposal. By continuing to explore and innovate, we can look forward to a world where materials are stronger, more durable, and better suited to meet the challenges of tomorrow. Moving on to Section 6, Gel Fraction Yield, a measure of success. How do we know if our irradiated copolymers are up to the task? This is a crucial question in the field of polymer science, especially when we are dealing with materials that need to perform under specific conditions. Well, one way is to measure their gel fraction yield. This measurement is a key indicator of the material's performance and reliability. Think of it like this. When we irradiate a copolymer, some of it might not fully cross-link. This incomplete cross-linking can affect the material's strength and durability. The gel fraction yield tells us how much of the copolymer has formed a strong, interconnected network. The higher, the better. This interconnected network is what gives the material its desired properties, such as elasticity, toughness, and resistance to solvents. The gel fraction yield is essentially a measure of the efficiency of the cross-linking process. A higher gel fraction yield indicates that a larger portion of the copolymer has successfully formed a network, which is crucial for applications that require high-performance materials. A high gel fraction yield means our copolymer is ready to tackle those dye molecules. This readiness is not just about the material's ability to interact with dyes, but also about its overall stability and performance in various environments. For instance, in biomedical applications, a high gel fraction yield can ensure that the material remains stable and functional within the human body. In industrial applications, it can mean better resistance to wear and tear, leading to longer-lasting products. The process of measuring gel fraction yield involves several steps. First, the copolymer samples are irradiated under controlled conditions. This irradiation process initiates the cross-linking reaction. After irradiation, the samples are subjected to a series of tests to determine the extent of cross-linking. These tests often involve dissolving the non-cross-linked portions of the copolymer and measuring the remaining gel fraction. The data obtained from these tests is then analyzed to calculate the gel fraction yield. This analysis provides valuable insights into the efficiency of the cross-linking process and the overall quality of the copolymer. By understanding the gel fraction yield, scientists can make informed decisions about the suitability of the material for specific applications. In summary, the gel fraction yield is a critical measure of success in the field of polymer science. It provides a quantitative assessment of the material's performance and helps guide the development of high-quality, reliable copolymers. Whether for biomedical, industrial, or other applications, a high gel fraction yield is a key indicator that the material is ready to meet the demands of its intended use. So the next time you come across a high-performance polymer, remember that its success is often measured by its gel fraction yield. This simple yet powerful metric plays a crucial role in ensuring that the materials we rely on are up to the task. Section 7. In the realm of environmental science, one of the most pressing challenges we face today is the effective treatment of wastewater. Swelling ratio, like a sponge for pollutants. Scientists have been tirelessly working on innovative solutions to tackle this issue, and one promising approach involves the use of copolymers. Copolymers can act like sponges, soaking up dye molecules from wastewater. These copolymers are specially designed to interact with pollutants at a molecular level, making them highly efficient in capturing and removing contaminants. The swelling ratio is a measure of how much liquid a copolymer can absorb. This property is crucial because it determines the capacity of the copolymer to hold and trap pollutants. A higher swelling ratio means the copolymer can capture more dye molecules. This is particularly important in industrial applications where large volumes of wastewater need to be treated efficiently. This ability is crucial for efficient wastewater treatment. By using copolymers with high swelling ratios, we can significantly reduce the concentration of harmful substances in the water, making it safer for discharge or reuse. Imagine a sponge that can hold a large amount of water. That's the kind of performance we're looking for in our copolymers. These materials are not only effective, but also versatile, capable of being tailored to target specific pollutants. Researchers are continually experimenting with different formulations and structures to enhance the performance of copolymers. By adjusting the chemical composition, they can create materials that are even more efficient at absorbing pollutants. Testing these copolymers under various conditions is essential to ensure their effectiveness in real-world applications. This includes evaluating their performance in different types of wastewater and under varying environmental conditions. The ultimate goal is to implement these advanced copolymers in large-scale wastewater treatment plants. By doing so, we can make a significant impact on reducing pollution and protecting our water resources. Clean water is vital for all forms of life, and by improving our wastewater treatment processes, we are taking a crucial step towards a more sustainable future. Copolymers, with their sponge-like ability to absorb pollutants, are at the forefront of this effort. Collaboration among scientists, engineers, and environmentalists is key to advancing this technology. By sharing knowledge and resources, we can accelerate the development and deployment of these innovative materials. The vision for the future is clear: a world where clean water is accessible to all, and pollution is a thing of the past. With continued research and innovation, copolymers could play a pivotal role in making this vision a reality. As we move forward, the importance of sustainable and efficient wastewater treatment cannot be overstated. Copolymers, with their remarkable ability to act like sponges for pollutants, represent a promising solution to one of our most critical environmental challenges. Section 8. Thermal stability. Taking the heat, wastewater treatment can get hot. Literally. That's why thermal stability is important. We need copolymers that can withstand high temperatures without breaking down. The more thermally stable our copolymers are, the longer they can operate effectively in demanding wastewater treatment environments. This durability translates into cost savings and a more sustainable solution. Section 9. Real-world applications from lab to life. The amazing properties of copolymers aren't just theoretical. They're already being put to good use in real-world wastewater treatment plants. These versatile materials are helping to remove harmful dyes from industrial wastewater, making our water cleaner and safer. It's a testament to the power of polymer science to solve real-world problems. Section 10. A cleaner future. The promise of polymer science. As we continue to explore the potential of copolymers, the future of clean water looks brighter than ever. These tiny molecules hold immense promise for tackling pollution and protecting our environment. It's a reminder that sometimes the smallest solutions can have the biggest impact.
Hey there, science fans. Today we're diving into the fascinating world of surfaces and what sticks to them. Ever wondered how charcoal filters water or how those little silica gel packets keep your new shoes dry? It's all thanks to a phenomenon called adsorption. Adsorption is like molecular Velcro. It's all about how molecules in a gas or liquid stick to the surface of a solid material. Think of it like this. Imagine a dance floor, our surface, and a bunch of eager dancers, our molecules. Some dancers prefer clinging to the edges, while others might venture further out. Now, how do we measure this molecular dance party? Enter adsorption isotherms. These handy graphs show us how much stuff sticks to a surface at a specific temperature, depending on the concentration of our dancers in the surrounding environment. In simple terms, an adsorption isotherm is like a report card for surfaces, telling us how good they are at attracting and holding on to specific molecules. Pretty cool, right? Let's meet our first contestant in the isotherm world, the Langmuir isotherm. Imagined by the brilliant Irving Langmuir, this model describes adsorption as a neat and orderly process. Imagine molecules lining up in a single layer on a perfectly smooth surface, each molecule finding its designated spot. The Langmuir model makes a few assumptions to keep things simple. It assumes that all adsorption sites on the surface are equal, and that once a molecule occupies a site, no other molecule can join the party at that location. This model is represented by a simple equation that's easy to plot on a graph. The graph helps us determine the maximum amount of stuff that can stick to the surface, which is super useful in various applications. Think of it like parking spaces in a parking lot. If all spaces are the same size and only one car can park in each spot, the Langmuir model helps us figure out how many cars the lot can hold when it's full. Now let's get real. In the real world, surfaces are rarely perfectly smooth and molecules don't always play by the rules. Enter the Freundlich isotherm, a model that embraces the chaos of real-life adsorption. Unlike Langmuir, the Freundlich isotherm isn't afraid of a little mess. It assumes that surfaces are heterogeneous, meaning they have a mix of different adsorption sites. Some spots might be more attractive to molecules, while others are less inviting. Moreover, the Freundlich model allows for multi-layer adsorption. Molecules can pile on top of each other, creating a molecular tower of power. This makes it more suitable for describing adsorption on rough or porous surfaces. Think of it like packing a suitcase. You can neatly fold clothes and arrange them in a single layer, Langmuir, or you can stuff everything in, creating multiple layers of clothes, shoes, and souvenirs, Freundlich. So, which isotherm reigns supreme? Well, it all depends on the specific situation. The Langmuir model, with its assumptions of a uniform surface and monolayer coverage, shines when dealing with adsorption on smooth, homogeneous surfaces at low concentrations. On the other hand, the Freundlich model, embracing heterogeneity and multi-layer adsorption, takes the crown when describing adsorption on complex, real-world surfaces, especially at higher concentrations. Imagine trying to model the adsorption of gas molecules onto activated carbon, a material with a highly porous structure. The Freundlich isotherm, with its ability to account for the diverse adsorption sites and multi-layer coverage, would provide a more accurate representation of the process compared to the Langmuir model. It's like choosing the right tool for the job. You wouldn't use a hammer to tighten a screw, would you? Similarly, understanding the strengths and limitations of each isotherm model allows scientists to choose the best fit for their specific needs. Now that we've met our isotherm heroes, let's see them in action. Adsorption isotherms are more than just theoretical concepts. They are powerful tools used in countless industries to design and optimize various processes. One of the most common applications is in designing effective filtration systems. Whether it's purifying water, removing pollutants from air, or separating different components in a chemical mixture, understanding how molecules adsorb onto specific materials is crucial for developing efficient and targeted filtration technologies. Imagine designing a filter to remove a specific toxin from drinking water. By studying the adsorption isotherm of the toxin on different filter materials, engineers can identify the material with the highest affinity for the toxin, ensuring its effective removal from the water supply. From cleaning up our environment to developing new materials, adsorption isotherms play a vital role in shaping our world. Let's talk about pollution, a major challenge facing our planet. Fortunately, adsorption swoops in as a superhero, offering sustainable solutions for environmental remediation. Activated carbon, with its incredibly porous structure and high surface area, is a champion adsorbent, capable of removing various pollutants from water and air. Imagine it like a molecular sponge, soaking up harmful substances and trapping them within its pores. Heavy metals like lead and mercury, notorious for their toxicity, can contaminate water sources, posing serious health risks. Activated carbon filters, utilizing the power of adsorption, efficiently remove these heavy metals, providing safe and clean drinking water. In air purification systems, activated carbon filters combat volatile organic compounds, VOCs, those sneaky pollutants released from everyday products like paints, furniture, and cleaning supplies. By adsorbing these VOCs, activated carbon filters improve indoor air quality and protect our respiratory health. As we transition towards cleaner energy sources, finding efficient ways to store energy becomes crucial. And guess what? Adsorption is stepping up to the challenge, particularly in the development of advanced energy storage technologies like hydrogen storage. Hydrogen, with its high energy density and zero emission potential, holds immense promise as a clean fuel source. However, storing hydrogen safely and efficiently remains a key hurdle. Enter metal organic frameworks, MOFs, a new class of materials with incredibly high surface areas and tunable pore sizes. These MOFs act like molecular storage units, capable of absorbing and storing large amounts of hydrogen within their porous structure. Imagine a tiny apartment building with countless rooms, pores, each capable of accommodating a hydrogen molecule. This high storage capacity, coupled with the reversible nature of adsorption, makes MOFs frontrunners in the quest for efficient hydrogen storage solutions. Section 8. Drug delivery on point adsorption's role in medicine. Now let's explore the fascinating world of medicine, where adsorption plays a crucial role in drug delivery systems, ensuring medications reach their targets effectively and safely. Imagine tiny drug carriers like miniature submarines designed to deliver medications directly to specific cells or tissues in the body. Adsorption plays a crucial role in loading these carriers with the drug molecules. By carefully selecting materials with specific surface properties, scientists can control the amount of drug adsorbed onto the carrier, ensuring a controlled and targeted release of the medication at the desired location. This targeted approach minimizes side effects and improves treatment efficacy, revolutionizing how we combat diseases. Section 9. Beyond the basics. Exploring other isotherm models. While Langmuir and Freundlich are the most famous duo in the isotherm world, there are other models out there, each with its own strengths and applications. The Temkin isotherm, for instance, considers the interactions between adsorbed molecules, assuming that the heat of adsorption decreases linearly with surface coverage. This model is particularly useful in describing adsorption on heterogeneous surfaces where molecule-molecule interactions play a significant role. The Dubinin-Radushkevich (DR) isotherm, on the other hand, is often used to describe adsorption in microporous materials, like activated carbon. It assumes a Gaussian distribution of adsorption energies, reflecting the diverse pore sizes and shapes found in these materials. These additional models provide a more comprehensive understanding of adsorption phenomena, allowing scientists to choose the most appropriate tool for their specific research or industrial application. Section 10. The future of adsorption, innovations, and discoveries. The world of adsorption is constantly evolving, with scientists and engineers pushing the boundaries of this fascinating phenomenon to develop new materials and innovative technologies. Nanomaterials, with their incredibly high surface areas and unique properties, are opening up exciting possibilities in adsorption-based applications. Imagine tiny nanotubes acting as molecular filters, removing even the smallest impurities from water or air. Researchers are also exploring bio-inspired adsorption materials, mimicking the intricate designs found in nature. Imagine synthetic materials that can selectively capture and remove specific pollutants from the environment, just like how certain plants absorb heavy metals from contaminated soil. The future of adsorption is bright, with endless possibilities for addressing global challenges in healthcare, energy, and environmental sustainability. Section 11. Conclusion: the power of adsorption in our world. From the everyday act of brewing coffee to the development of life-saving medications, adsorption plays a fundamental role in shaping our world. Understanding the principles of adsorption, particularly the insights provided by isotherm models, allows us to harness this powerful phenomenon for countless applications. As we continue to explore the intricacies of surfaces and their interactions with molecules, we unlock new possibilities for innovation and discovery, paving the way for a cleaner, healthier, and more sustainable future. So the next time you see a silica gel packet or hear about water filtration, remember the incredible power of adsorption at work. Hello, I'm Professor Dr. Salah Lotfy from the Polymer Chemistry Department at the National Center for Radiation Research and Technology, Cairo, Egypt. Today, I want to share with you the exciting conclusions from our latest research published in Polymer Bulletin. Our study focused on the free radical polymerization of polyvinyl butyral, PVB, and polyethylene glycol diacrylate, PEGDA, copolymers, utilizing gamma irradiation for the removal of organic dyes from wastewater.
I'm Professor Dr. Manal Fawzy Abou Taleb from the Chemistry Department, College of Science and Humanities, Prince Satam bin Abdul Aziz University, and also a proud member of the National Center for Radiation Research and Technology in Cairo. Let's delve into our findings.
We observed that the gel fraction of PVB-PEGDA copolymers increased with higher irradiation doses. Additionally, the swelling behavior of these copolymers tended to increase with the molecular weight of PEGDA. The thermal stability of the copolymers was significantly enhanced by gamma irradiation, the presence of PEGDA, and the increasing molecular weight of PEGDA.
In our sorption experiments, PVB-PEGDA copolymers demonstrated high sorption capacities for the diamine fast scarlet GG dye, especially those with higher PEGDA molecular weight.
For diamine fast scarlet GG dye, the Freundlich model provided a better fit, suggesting a heterogeneous surface and multi-layer adsorption. Conversely, the adsorption of direct pink 3B was best described by the Langmuir model, indicating monolayer adsorption on a homogeneous surface. Thermodynamic analysis revealed that the adsorption of diamine fast scarlet GG onto PVB PEGDA is both spontaneous and exothermic, confirming it as a physical adsorption process.
Our research concludes that PVB-PEGDA copolymers are effective adsorbents for removing anionic dyes from wastewater, with potential applications in environmental cleanup.
Thank you for watching. We hope our findings contribute to the advancement of polymer chemistry and environmental science. together advancing science for a cleaner future.
We live in a world built on polymers. They make up the plastic bags we use at the grocery store and the rubber in our car tires. Scientists are now exploring the remarkable potential of polymers to solve one of humanity's most pressing challenges: clean water. Water pollution, particularly from industrial dyes, poses a serious threat to ecosystems and human health. Researchers are developing innovative polymer-based materials that act like molecular sponges, effectively removing these harmful dyes from wastewater. This isn't science fiction. It's the power of chemistry at work, offering us a tangible way to clean up our planet. By manipulating the structure and properties of polymers, we can create materials specifically designed to target and capture these microscopic pollutants, paving the way for a cleaner, healthier future. Imagine building a Lego tower. Creating specialized polymers for water purification follows a similar principle. We begin with smaller molecules, our building blocks, and use a process called free radical polymerization to link them together. In this molecular construction project, two key players take center stage: polyvinyl butyral, or PVB, and polyethylene glycol diacrylate, or PEGDA. PVB provides a robust backbone for our polymer, while PEGDA enhances the polymer's ability to interact with and capture dye molecules. Free radicals, highly reactive molecules eager to form bonds, act as our molecular glue, initiating the polymerization process and creating a copolymer. Now, imagine giving our Lego tower an extra dose of strength and durability. That's precisely what we achieve by introducing gamma irradiation into the mix. When we expose our PVB PEGDA copolymers to gamma irradiation, something remarkable happens. The gamma rays interact with the polymer molecules, causing subtle but significant changes in their structure. This process, known as cross-linking, acts like reinforcing our Lego tower with extra bonds. The result? A more robust and efficient material, enhancing the copolymer's mechanical strength, thermal stability, and resistance to degradation. Section 4. Swelling and stability. The power of PEGDA in action. Imagine building a tower with special bricks that can absorb water and expand, increasing their size and surface area. That's precisely what the PEGDA component brings to our PVB PEGDA copolymer. When our copolymer comes into contact with water, the PEGDA segments act like tiny magnets, attracting and absorbing water molecules. This absorption causes the copolymer to swell, increasing its volume and creating a more porous structure. The increased surface area and porosity create more binding sites for dye molecules, allowing the copolymer to capture and hold on to a larger quantity of pollutants. Section 5. Trapping the color culprits dye removal with PVB PEGDA copolymers. Now, let's put our super-absorbent gamma-irradiated copolymer to the test. In the lab, scientists use a model dye called diamine fast scarlet GG. When we introduce our PVB PEGDA copolymer to a solution containing this dye, the magic of adsorption begins. Our copolymer, with its enhanced porosity and surface area, acts like a magnet for the dye molecules, effectively removing them from the solution. The once vibrantly colored water begins to clear, demonstrating the remarkable efficiency of our polymer-based purification system. Section 6. Decoding the dance of adsorption. Freundlich and Langmuir take the stage. Understanding how well our copolymer removes dyes is one thing, but to truly optimize this process, we need to delve into the intricacies of adsorption. Two famous models, Freundlich and Langmuir, help us decipher the dance between adsorbent, our copolymer, and adsorbate, the dye. The Freundlich model describes adsorption onto surfaces with varying energy levels, suggesting that not all binding sites are created equal. The Langmuir model, on the other hand, assumes a uniform surface with identical binding sites. Analyzing the adsorption data through these models reveals valuable insights, allowing us to fine-tune the properties of our copolymers and optimize their dye removal efficiency for various applications. Section 7. A cleaner future. Thermodynamic triumphs and environmental promise. Beyond the lab, the real-world implications of this research shine brightly. Favorable thermodynamic values indicate that the adsorption of diamine fast scarlet GG onto our PVBB PEGDA copolymer is a spontaneous and energetically favorable process. These findings have profound implications for environmental remediation, allowing us to clean up industrial wastewater and remove harmful dyes before they contaminate our rivers and oceans. Picture a future where access to clean water is no longer a luxury, but a reality for all, thanks to the power of polymer chemistry. This research represents a significant step towards a cleaner, more sustainable future, paving the way for a brighter future for generations to come.